do you need to go from this to this? Because this is a relatively complex resistor network, I thought it might be fun and useful to model it on one of the circuit modelling websites. So I'm using PartSim for this. So you can see I've built the resistor network up, and what this enables me to do is to attach a voltage supply, which is going to be 12 volts, and we can measure the current and the voltage there across the whole network. Then we can solve it using the method I'll show you soon, and then check out if my answer for this agrees with the solution that I get algebraically in a minute. So what we'll do then is press run and see what happens. And then I press the next run, and this will give us a rather interesting looking graph. So two things going on in this graph. Firstly, the graph is showing that when I run the circuit, that first of all it starts off at 0 volts from the power supply, and it turns on, goes up to 12, stays at 12 for quite some long time before turning off again and going back down to 0. Here's the current trace, and you can see that at the start, just before the voltage goes up, it's 0, which is what you'd kind of expect. Then bang, up goes the current, and it stays constant at 4.667 milliamps. So about 4.7 milliamps. In other words, if I get one resistor to replace all of those other resistors, it needs to be of such a size that 4.667 milliamps will be the current that flows. Here we have the actual circuit drawn out as it was in the question. And we'll start off now by looking to see, are there any resistors that we can really definitely say are in series or parallel? And then we could deal with them first. Well, clearly these two are very much in series. So we can get rid of this one and just add them together, and this now becomes 2R. So if we were to re-sketch out that little triangle in the corner, it has now reduced to two resistors in parallel, one of which is 2R and the other of which is R. Now we have to reach for our parallel resistors formula. 1 over RT equals 1 over R plus 1 over 2R, which means that 1 over T equals 2 over 2R plus 1 over 2R, which equals 3 over 2R. And this then means that RT is going to be equal to 2 over 3R. So that means that we can replace all three of these resistors in this triangle with one that is 2 over 3R. And of course this here is the same identical triangle, so we can do the same with that one as well. Here, as they say, is one I did earlier. Next step then is to realise that the two 2 over 3R resistors are in series, so we can just add those two together, which is going to give us a 4 over 3R. And it's time to reach for our trusty parallel formula again, because our new 4 over 3R is in parallel with this resistor here. So let's do that. 1 over RT is 1 over R plus 1 over 4 over 3R. Now, we don't like this last fraction because it's a triple decker and we don't like those. So this now becomes 1 over R, doesn't change, and this becomes 3 over 4R. So of course 1 over R is the same as 4 over 4R. So in other words, 1 over RT becomes equal to 7 over 4R. Okay, that's not T, that's 1 over T, which therefore implies that R total is going to be equal to 4R over 7. That means we've now replaced those three resistors we were looking at with one of 4R over 7. And that leaves us with a much simpler circuit, which is very simple, like this, which is just three resistors in series. These two are both R, and this one is 4R over 7. So if we have to add those together, so we have R plus R, it's not too difficult this bit, plus 4R over 7. So adding those fractions together, each one of these, remember, can be written as 7 over 7. So we add those together, we actually have 14 plus 4, which is 18 over 7r. So this, in fact, is our answer. And what it's telling us is that whole complex network that we were looking at the start can be replaced with one resistor which has a value of 18 over 7r. But is that correct? Recapping then, you might recall that we started off by building a simulation circuit and getting a current of 4.667 milliamps flowing with the network. Now what I did in that was to set all the resistors to 1 kilogram. So R in our diagram is going to be 1000 ohms. And the voltage was set to 12. And that was when the current was equal to 4.667 milliamps. So what we've worked out is that we can replace all the resistors in the second diagram with one simple resistor that has a value of 18 over 7 times R. And R we set to 1000 ohms. So in other words, we should have 18k divided by 7 is going to be our resistance. So reaching for Ohm's law, we know that V equals IR, which implies that the current is going to be equal to the voltage divided by the resistance, and the voltage is 12 divided by 18,000 over 7. Well, or we could rewrite that if you want as 12 times 7 over 18,000. So now it's time to reach for the calculator. And he's back from reaching for his calculator, and hey presto, that does indeed come out as 4.667 milliamps if you go to the same number of significant figures. Okay, so what we've proved here, the simulation has proved for us that mathematically we have handled this resistor network correctly when we get the value of 18,000 over 7, or 18R over 7, perhaps I should say. You might be wondering, why did I bother with running a simulation here? Well, basically because I was finding this question, I was going round and round a little bit trying to get the right answer out. And it's not because I doubt my physics, it was more about getting the answer into exactly the right form that the website needed for me to get a tick rather than a incorrect. In actual fact, I was getting it right when I was using values rather than decimal values, that is, rather than fractions, but the website was telling me I wasn't. So really the simulation enabled me to just get that kind of little bit of reassurance that perhaps I needed, that I wasn't going and doing something silly. So even physics teachers need reassurance from time to time. Hope you found that useful. Please don't forget to share it with all your friends. Bye.